I want to reflect on some of my own experiences involving NBS, NIST, and Fano, and bringing atomic physics and solid state physics a little bit together. This is the excerpt from Jerry Mann's book, which I have in my abstract in the meeting. The point of Jerry Mann's book, or of Jerry Mann, who is a very distinguished solid-state theorist, is that this model Hamiltonian, which has characterized by a discrete state, a continuum, and a coupling between the two, was introduced simultaneously by Phil Anderson in '61 and Fano in '61. And Anderson applied it in the domain of solid-state physics to magnetic impurity problems, and Fano, you all know, applied it to atomic physics problems. And depending on your cultural origins, you either knew it as the Fano model or the Anderson model. And Jerry says, well, we'll call it the Fano-Anderson model. Now, I came to myself to, well, okay, let me just say how we're going to occupy our time for as long as the Hossein lets me. We're going to talk about this issue of the Fano-Anderson model as a showcase for atomic versus solid-state physics, or what issues there are in common and are different. I'll reflect on the Fano and NBS in the '60s, which is when his famous paper was done. Now, I was in grad school at MIT in the '60s. I came to NBS in '68 from a solid-state physics background, and it was just a eye-awakening experience for me to see all this atomic physics, which I had been somehow insulated from as a grad student. Okay, so we'll talk about something about the '60s. There was some particular work that Ward Plummer and myself and Russ Young were involved in, involving resonance tunneling and field emission, which presented a very good vehicle for describing some Fano-Anderson effects, which were somewhat amusing also. And they have are now there's a current incarnation of this kind of thinking in the STM condo models of this of the current generation, which Mark Kastner and Ned Wingreen will talk about. We'll talk a little bit about then what's new about condensed matter physics with respect to atomic physics. The fact that you're condensed means you have neighbors, which means that if I have something on an atom, it can delocalize. We have continuum in solid-state physics, which is bounded. It doesn't. The energies don't go up and down forever, and that has effects, and it has a structure in the continuum. And there's a big, well, I say big U effect, localization, which is the Coulomb interaction between up and down spin electrons, which lead to well, important effects. So NBS in the 40s through the 60s, was, at least from the point of view of atomic physics, was dominated by the man. He was the intellectual spirit of all the atomic, or most of the atomic physics work, it seemed like to me, that was going on at the time. He was, well, okay. This is a poster from a talk that he gave in '96 at the time when he received the Enrico Fermi Award. Okay, so NBS through the 60s. We may get a chance to come back to how things have changed. Okay. Just by way of review, there are these class of papers that are widely cited. Also, the results are used, but rarely are they read. And just so you can say that your eyes have been on the Fano paper, this is the beginning of it. The point is that the model involves a discrete state, coupling between a discrete state and a continuum, and there's an eigenstate, the perturbed continuum, which is a combination of the discrete state and the unperturbed continuum, as Hossein pointed out. A point that is important for solid state people is this A coefficient, the mod square of which is something that looks like some sort of perturbed Lorentzian. And I'll give you a hint that if I say local density of states, the solid state people will, their ears will perk up. We also saw that in the paper, what was one of the big outputs of the paper, of the 61 paper, was the Fano line shape, in which this line shape was the if you consider a process in which I made an excited state, some initial excited state called I, and it was coupled to this perturbed continuum, this continuum in which there was an embedded discrete state. The ratio of the transition of the amplitude squared for that, the decay into the perturbed continuum divided by the decay into the unperturbed continuum, was the Fano line shape, in which Q, the asymmetry, the Fano parameter, was basically a measure of the coupling of the excited state to the discrete state with this admixture over the excited state to the unperturbed continuum, and one got this family of curves. Okay, so this is the buzz. Now, as I say, I was just a naive little solid state person who came to this. There was all kinds of activity. Fred Meese's work was mentioned. This is also okay. There are a couple of beautiful things. Okay, the purpose of the present study is to extend Fano's CI theory. It is felt that the CI theory, warrants a detailed development. So one of the things that Fred was considering then was a situation in which an electron scattered from a molecular system, either directly or via a resonance channel. So there's a direct process and a resonance process, and the two could interfere, and interferences mean Fano line shapes. So this is going on in my mind. I'm digesting this. Okay. Equal time. This is the Anderson paper, which was in the same volume of Physrev as Ugo's paper. Actually came out a couple months earlier, and Anderson's paper was titled "Localized Magnetic States in Metals." He formulated the problem in terms of a Hamiltonian, in which the first three terms were the terms that I talked about, that Jerry Mann mentioned, and there was an additional term, a correlation term, which took into effect the fact that in a solid, the discrete state and the impurity atom, which was embedded in this continuum, could have one electron, or could have half an electron of upspin and half an electron of downspin, and energetically those were different, and that possibility gave rise to the possibility of localized magnetic moments on the impurity atom. Okay, so this is just to give you a flavor of how the solid state stuff looked. Again, here's the key to it. The Fano perturbed continuum is a discrete state plus the unperturbed continuum. Anderson expressed it in this way. You can see perhaps this Lorentzian-like thing, which is a density of states. Okay, so that's the background. Now, this is a little bit interesting, just from the current physics point of view. I came to NBS into the electron physics section of the atomic physics division, and there was some small amount of surface work going on which was related to trying to make electron beams for atomic physics, amongst other things. This was John Simpson and Chris Kuyat were the electron beam people, and then in Madden and all those were doing the atomic physics. One of the experiments was a field emission experiment in which Plummer was a postdoc with Russ Young. They had a field emission tip. This is a little tungsten wire about 1,000 angstroms in diameter, and that tip was put about 1 centimeter from a fluorescent plate. And if you applied a field between the tip and this electrode, you got a potential barrier that bent down, and electrons could tunnel from the tip to outside the field. Now this field was about a few tenths of a volt per angstrom, so this tunneling distance between the edge of the surface and outside was 10 or 20 angstroms. Now, what could be done then was in this fluorescent screen, if they made a little hole, they called it a probe hole, then the electrons that tunneled from this tip and went through that probe hole, this probe hole accepted electrons that were tunneling from about a very small area on the surface, 10 or 20 atoms on the surface. So you saw what was happening on a very small patch. Now, they had this in a vacuum and turned on a gas source. So some gas was in the ambient, and measured the current through that probe hole as a function of time. So they turned on the gas source. The evaporator is on. At some point, an atom arrived on the surface and got to the area on this tip that was emitting through the hole, so that there was when that happened, there was a discontinuous jump in the current when a single atom arrived. Now this is in the late 60s. So then they turned the evaporator off and it was stable, and then turned it back on, and then in a while another atom arrived and there was another jump. So what was happening? There was reason to believe that there was some that atoms on the surface, if they had energy levels that were in the vicinity of the Fermi level, that electrons could tunnel from the tip into the atom, resonantly, and then from the atom out. And because this barrier from the atom to free space was much less than from here to there, you would see an enhancement in the current. And so so this was measuring the arrival of a single atom. Then you could do an energy distribution of those electrons that pass through there, and you could see how the electrons that were tunneling through the single atom were distributed in energy. We made a so we had a model for this, in which basically watered down theory said that the matrix element for these resonance processes were a direct term. We could go right from the metal, a metal electron out, and there was possibility of a resonance term from the metal into this resonance. We're in a resonance state, so there's a resonance denominator, and then from the atom out. And the observations, the current would be the square of that, and you could see that there would be a direct term. There would be a term that would be mainly from the atom out, and an interference term. Now, because the amplitude for going from here out, these amplitudes depend on the exponential decay of electron wave functions. This was much more favored than that. So the square of the resonance term dominated the behavior. But anyway, we saw that this was could show a Fano like shape. And this just sort of summarizes it all. But our energy distribution was, the line shape was, we cast a theory in a way in which we could have it look like the local density of states on the atom, which is the Lorentzian, divided by the continuum density of states, times what amounted to a Fano Q factor, the square of the Q factor, which is the dominant term. In the Fano theory, in the limit of large Q, this is what you get. And this was the first spectroscopic measurements of an electron energy level distribution for atoms on a surface. Now, we were happy about this, and Fano was periodically would visit NBS to nurture the people, and so an atomic physics division colloquium was set up. I was going to give a talk on this when he was there, so that he could pass judgment, and there was also the hope that maybe he would give his blessings to our surface work. So I gave this talk in which I gave it some particular name, and I developed everything in a parallel in two columns, Anderson and Fano, because coming from the solid state background, that was where I had worked, but I tried to translate that into Fano theory, and so this is basically how the slide looked. For every Fano thing, there was an Anderson equivalent, and well, he didn't care much about didn't pay much attention to our resonance tunneling. This apparently was the first time he had seen the Anderson work, and I got lambasted by him more or less. Well, not lambasted, but I had to be very defensive about the Anderson thing. Where did this come from? Where did this come from? And I felt really terrible. But ultimately I got an invitation to come to Chicago to give the talk. So I guess it didn't go that badly. So that was kind of amusing. Then we'll hear of the work of the modern view of this work. Ned Wingreen will talk about this, in which, as was mentioned, in doing these STM experiments, one sees these Fano line shapes that whose symmetry varies or asymmetry varies as a function of the tip position. Now, this is quite nice, but then it does prompt an unreasonable question, not unreasonable question, which is, are the STM Fano line shapes, are they interesting or important and useful? And I guess at least my view of the answer is, well, we're interested in them. But if they're useful, I mean, okay, are we going to get some new information out of them? It's because there is new information in the STM tip position dependence on Q, and so you must understand you can't use Q just as a fitting parameter, which a lot of solid state people in a lot of the solid state applications you see out there now, people, if they see an asymmetric shape, they fit it to a Fano shape using Q as a parameter. Well, you can do that, but it's not. That doesn't gain you any new information unless you understand the physical content. And Ned will, I'm sure, talk a bit about that. So let's then ask this question again. What's new about condensed matter physics, at least as far as Fano line shapes are concerned? And as I said, well, condensed means neighboring atoms, and so there are localization, delocalization issues. These compasses are a result of font incompatibilities between between what I typed and what the printer printed. But anyway, one of the important things about the solid is, okay, we have the continuum in a solid, the conduction band, in case of metals, the conduction band states of metals are states whose energy, the quantum numbers for the energy are wave number. So E versus K is the band structure. And there's a bounds on this. There's a lower energy below which there's no band, no conducting states, and above which there aren't any. And also, I mean, if you are a discrete state embedded in this continuum, if you are near the edge of this bounded continuum, there are going to be some edge effects which will have can have observable consequences. Now, the question of Fano resonances, at least within my experience within the solid state world, is people intermingle two things. You know, the discrete state, which is broadened by interaction with the continuum. Some people, to them, that is a Fano resonance. That is the mod a square term in Fano language, which is the local density of states in solid state language. This is a signature of a system, a signature of an impurity system or adsorbate or whatever. The Fano line shape is another thing which can be called a signature of a Fano resonance, but that's a signature of a process. Now, of course, that process is often, whether it's photo emission or whatever it is, has been undertaken to try to get some information about the system, so that you might see a resonance of this sort in your attempts to understand that kind of resonance. Okay, so I want to show a particular example of how some of this works out. It's a very simple, almost textbooky kind of example, but how one might go between the two camps, between the atomic physics and chemistry type of camp and the condensed matter. Suppose I have a lattice, a solid state system. Okay, let's say with the surface, and I'm going to ask myself, I'm going to interact an atom, say an S, in this case an S-like atom, with the surface to form some kind of bond. Okay, I have a solid, so I have an energy band E versus K, which looks like so. This is the continuum. It has a maximum and a minimum energy. Forget about that for the time being. I have this discrete state, the atom, which has some energy, and let's say it makes sense if this is suppose it's a D band. Okay, D band material. So I have orbitals like so. In this case, this orbital will not. This will be a non-bonding situation with respect to these two babies. Whereas if the phase of this is reversed, so I'm here, I have a bonding combination. So therefore, if I interact my atom with this bonding situation, I may get a bonding and an anti-bonding combination, a localized thing, whereas in this case nothing happens. So I start off with a group orbital has a certain energy, and it doesn't change as a result of interacting with this discrete state. So I have that atom interacting with the group orbital. I get a bunch of shifted discrete states, which now I embed in the continuum. And what happens? Well, I may this state lies below the bottom of the continuum, so it'll be a localized state. This state is embedded in the continuum, so it spreads out throughout, but it has a peak somewhere within, and maybe and this might be on top of the continuum. The solid state continuum states are block functions, which can be written in a tight binding way. The discrete state is some very small sum of orbitals like so. And when I go to do my VAK, which is in the resonance theory, if I imagine that this localized atom, the discrete state, interacts mainly with the group orbital G, which then projects onto the K. I've separated this into the product of a localized thing times a delocalized thing, and so the level width function is now the if I go through these manipulations, is the product of the overlap of a hopping integral between localized functions times a projected local density of states, like so. And I have an example worked out in which I have considered an S adsorbate versus a P adsorbate, or an S-like discrete state and a P-like discrete state, and work out these projected local density states for a tight binding band, which is like a cosine. And the projected densities of states are that. The numerical, okay, so how this looks is the following. For the S adsorbate on this P band substrate, where the continuum goes from -1 to 1, the level width function is something that is 0 at the band edges, rises up to a maximum in the band center, whereas for the P adsorbate on the same band, the maxima are at the edges with 0 in the center. The level shift function is the Hilbert transform of this, which is these things. The local density of states, or the resonance, is this Lorentzian-like thing where the level width and the level shifts are actually functions of energy. And for this particular case, for resonance, which originally is say a quarter above the center of the continuum, we see that for the S adsorbate, there's a spread like so, with a localized state split off the band, whereas for the P adsorbate, there's states split off both on the top and the bottom, and a peak in the middle. So there are considerably different things happening. My last sort of comment on other sorts of things are the effect of the E square of the correlation, the E square electron-electron interaction term. In atomic physics and Fano theory, the emphasis has been different. You use it to describe the configuration interactions, autoionization. In the case of condensed matter physics, like in the Anderson model, big U, which is the Coulomb interaction between up and down spin interactions, that gave rise to things like localized magnetic moments and Kondoology, which we're going to hear in the next two condensed matter talks, and things like Mott transitions and whole localization. So I think that that sort of gives you a flavor for the condensed matter types of things that the Fano work has sort of inspired. Now, this was, NBS in the 60s, very dignified sort of situation. Ugo has given rise, has his intellectual products, and of which some of them are, a lot of them are at NIST, and this is just sort of an example of sort of NBS NIST currently, and that's what it's all led to. So I thank you very much.